Please put your hands together for your host, Greg Foote.
Oh, hi everybody. Morning, how are you? You're far too quiet. Morning, how are you? That's more like it. Welcome to the IET's Engineering Open House Day! Oh, it's good to have you back in the room, isn't it? It's good to see you here in Savoy Place. We've got lots of people watching online as well. Hello, hello. Do you want to turn around and wave at the camera at the back and say hello to everyone watching online? Hello, everyone at home. Hello, 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 hello. So I just came on and said hello and welcome to the IET's Engineering Open House Day. What is Engineering Open House Day? I hear you say. Someone knows. It is all about a celebration of how awesome science, technology, engineering, and maths is. Something that we sometimes shorten to STEM. Science, technology, engineering, and maths. So that's the idea for today. It's for all of you lot to discover the huge variety of exciting, creative jobs in the world of STEM. From working on Formula One cars, to getting rockets up into space, to saving people's lives. STEM's really exciting. In fact, hey, here's a question. What would your dream job in STEM be? Would it be in sports, music, travel, fashion, helping, maybe improving the health of people or the health of the planet? Turn to the person next to you and tell them what your dream job in the world of STEM would be. And this is also for you lot watching at home, okay? You do the same. What is it? Tell the person next to you. And then turn around and tell the person on the other side of you. And if it's a chair, tell the chair. Brill, okay. I heard some great ones. I heard some amazing ideas. You lot have got some fun adventures on the way, I tell you. That's cool. So that's what you might be doing in the future. Shall we discover what you're going to be doing in the near future? Let's find out what's going to happen in the next 45 minutes to an hour-ish, shall we? Okay, cool. Right, coming up today, things are going to get hot when Dangerous Dan takes to the stage and shows us the fundamentals of fire. That's going to be very cool. Or not, it's going to be hot. Yes. Then we're going to meet the brilliant Kira McGrath, who is the Young Woman Engineer of the Year, no less. She's going to tell us everything there is to know about spacecraft. How do you launch them? What do they do? How do you get them back? She's even brought a spacecraft for all of you lot to me, which is very, very neat. What else? You're going to hear from a whole bunch of different awesome engineers today. I'm going to tell you about a STEM adventure that I got to go on, diving into the deep, dark ocean. That's coming up very soon. And at the end of the show, I'm going to choose a few of you who want to come up to play an engineering game on the stage. That's the plan. There's loads of other stuff going on here as well for Engineering Open House Day, here at Savoy Place and all over the UK as well. If you go outside, if you take part in the exhibits, take some photos, get the grown-ups to put them on social media, use the hashtag #IETOpenHouse. If you squint, you can see it right in the corner of the screen. Okay, shall we get this show started? Shall we get this show started? Put your hands together, clap your hands, make some noise for the one, the only, Dangerous Dan!
Thank you very much. Good morning, everybody. My name is Dangerous Dan, and we are going to be doing some fun, mad science today. So, the fundamentals of fire. For fire, you need 3 ingredients. Does anybody here think they know what the ingredients for fire are? Just give me one. Yes. Oxygen. Fantastic. Straight away. Would you come up here with me, please? I need you right up here. Yes, oxygen. Everybody take a nice deep breath in. Ah, delicious oxygen. Little did you know that that is one of the important elements for fire. What's your name? Nikhil. You are going to stand right here. Perfect. You are oxygen. Very, very important. 20% of our atmosphere. What you are going to do is every time I say oxygen, you're going to do this. Oxygen. Are you ready? Oxygen. Oh, fantastic. Look at that. Fantastic. Round of applause, yes. I think we are missing 2 more elements because at the moment oxygen's not enough. Yes? Oh, this is amazing. Fantastic. Yes, heat. Will you come up as well? Anywhere you like. Look at that, just jumping straight off the bat. Heat. You cannot have a cold fire. You must have heat. Now, heat, of course, is very, very hot. So you're going to stand right here, and you are going to pretend your feet are on fire. So every time I say heat, you're going to do this. Heat. Oxygen. Fantastic. Now we are missing one thing, because at the moment, with heat and oxygen, we've got warm breath. We need something else. One last thing. What could it be? Yes? Oh, this is amazing. 3 right answers straight away. Fuel, absolutely. We normally get loads of answers. Yes, come on up, come on up. We normally get sticks and matches and oil and potatoes, whatever. Loads of people say loads of crazy things when they think of fuel, but they are all one large category, and that is fuel. Now, this is anything that burns. So because you are fuel, you're going to do this. Fuel! Are you ready? Fuel. Heat. And oxygen. Fantastic. These are our 3 elements of fire. Without them, there is no fire at all. They know who they are. So what you're going to do is when I place my hand above their head, you are going to shout out which one they are, and they are going to do the actions. Are you ready, audience? Yes. Are you ready, people on stage? Yeah. Good. Okay, here we go. Fantastic. Yes. Perfect. Now we have our 3 elements. But if we take any of these away, we extinguish our fire. If you take away our oxygen and all you have is heat and fuel, you just have warm things. No fire. This is like having a fire in space. You must have oxygen. If you take away the fuel and all you have is heat and oxygen, this is just warm breath. You have to burn something. And if we take away the heat and we just have oxygen and we just have fuel, well, that's everything in this room. So it's a good job that it's not on fire. So I think a round of applause for our 3 excellent elements of fire. Well done, well done, well done. You've been brilliant. 3 right answers straight off the bat. So I think it's about time we set something on fire. Let's light my candelabra up here. Oh, it's getting romantic already. This. Fantastic. Problem is, fire is dangerous, and so we must be at least a little bit careful. So I have to try and keep myself from catching on fire. I'm going to need a fire extinguisher. Luckily, I brought one right here. This is my lovely fire extinguisher, my lovely bottle. I'm going to fill it full of a little bit of water so that we can put out our fire, and then we're going to stand a good distance back. We're going to try and attempt to put out the flames. Are you ready? Nothing. I must be doing something wrong. How am I going to get the water out of this bottle? Does anybody have any ideas? Yes. Squeeze it. It is a solid bottle, unfortunately. It does not squeeze. Must be something else. What could we do? Pardon? Pour it out? Well, then I wouldn't be able to put out the flames. I must need to do something to get a little closer. Anybody at the back? Yes. Open the lid? It doesn't seem to have affected the flames at all. We've got one more thing. What can we do? I'll take one more sensible suggestion. Yes. Squeeze the top. No, that doesn't seem to be working. Go on. Poke a hole in it. There's already a hole in the top. No, the answer is obvious. It is?
You tip it upside down. Gravity?
Gravity. Well, gravity won't work too far away. The obvious answer is I just need to shake it. Like this. Ah, it is working. There we go. Look at that. With just a little shake of the bottle, it spurts out nice and easily. Let's see if we can put our flames away. Oh. Perfect! Ah, I feel safer already. Now, this worked because this is not just normal water. This is carbonated water, fizzy water, sparkling water. That means all these little bubbles inside here, those are bubbles of carbon dioxide. And as we shake it, they rise out of the water and expand, creating enough pressure that it pushes the water out and is able to shoot across the room, get you guys nice, wet, and put out the flame. So now we are nice and safe. I think we should introduce you to a good friend of mine. This is Egbert. Say hello to Egbert. Egbert is an egg, a very greedy egg, and unfortunately his breakfast has been so large he now no longer fits in his home. So, how are we going to get Egbert into his house? Yes. A burning thing in the beaker? If you couldn't get into your house, I wouldn't set the things inside of it on fire. That'd be terrible. Yes. Push it down. I don't think so. I think if I push him, he's going to break. Yes, right at the back. Yes.
Chuck it on the floor.
Chuck what on the floor? Egbert or the very, very delicate glass? Yes. Pardon? Heat the beaker. Well, I don't have any gloves. I don't want to burn my hands. I'll take one more excellent suggestion. Yes? Heat the egg. Well, the egg has already been boiled, so I don't think we're going to heat him anymore. I think the answer is obvious. We are going to give Egbert a haircut. A haircut, yes, a very, very special haircut. This particular haircut is the Flaming Mohican. Here we go. We'll just finish it off. Ah, perfect. Meet Egbert's spectacular new hair. Look at that. But it is not quite complete. I think we need to finish it off with a little bit of fire. Excellent. Now we have our excellent Flaming Mohican. We'll see if we can get Egbert into his home. Are we ready? Perfect. Look at that. A perfect dismount right into his house and a little flip right at the end. Now we have Egbert perfectly inside his bottle. Does anybody know how this worked? No? Well, it is quite simple. Remember that oxygen we were talking about? That is also in the bottle. So what we did was we set fire to all of the oxygen in the bottle, and as soon as it was all depleted, then we created a vacuum. That vacuum pushes from equal sides. I was going to say, I feel very quiet all of a sudden. Thank you very much. So we managed to create a vacuum which sucked him inside. Is this even on? 1, 2. Doesn't sound on. No.
It's going well, I think. We'll
It's all right.
Sorry, Egbert.
Is it this?
Is it this? Is it me?
Is it there? No. It's got a green light. Hey, we're back. Fantastic. So we managed to create a vacuum, and that pushed Egbert from all sides equally, sucking him into the Erlenmeyer flask. So how do we get him out? Anybody know? Yes? Break the glass? This is Egbert's brand new house. He's only just got inside and already want to demolish part of it. No. Yes? Shake it. No, that only works with the fire extinguisher, unfortunately. Do it in reverse. Oh, that's not a bad idea. I think what we're going to try and do is we're going to try and put more air inside the bottle to create more pressure inside the bottle. Now, this is going to be done in a very simple way. I'm going to blow inside here, and this always goes one of two ways. I either end up with an egg in my mouth or with it very slowly sliding outwards. Let's hope for number 1. Are we ready? 1, 2, 3. Ugh. Great, the egg in the mouth. Ugh. So now Egbert is out of his house. I think we should go on to our final, nice, big, exciting experiment. This one is called the Great Fire of London. Who knows anything about the Great Fire of London? Where was it? When was it? Who started it? Was it you?
It was 1666.
Very good, 1666.
And it was caused by a baker who dropped red hot ashes onto the floor.
Very,
Bakery because he was distracted by a thief.
very possibly. Oh, that's the whole story, isn't it? But I think once we know when, where was this Great Fire of London? Yes. In Pudding Lane. Fantastic. Yes, Pudding Lane, Thomas Farriner's bakery. So what makes a bakery so explosive, so very dangerous that it would set fire to everything? Now, this is London in 1666. All the houses are made of wood. There's no electric heaters, so everything works off fire. So there's ovens and fire pits in everybody's homes. So there must be something a baker uses that is particularly flammable. Does anybody know what it is? A tea towel? It's a good suggestion. They probably are quite flammable, but not spontaneously. Yes? Flour. Oh, round of applause. Yes, flour is incredibly volatile. And we are going to use something a little bit more delicious today. It begins with an S. Put it in your tea. It's sweet to the taste. It's white powder, looks a bit like flour. It ends with a yugar. Anybody? Sugar, yes! We are going to be using sugar in particular, the most dangerous of the sugars. Icing sugar. Dun, dun, dun. Yes, icing sugar, the incredibly flammable. So we are going to place it here. I am going to take another match, and we are going to set all of this icing sugar on fire. Are you ready? 3, 2, 1. Oh. Nothing happened. We are fine. I still have my eyebrows, and there was no big flame. What happened? What are we missing from this experiment? Yes, the oxygen. Absolutely. We have our heat, which is in the match. We have our fuel, which is the sugar. We do not have any oxygen. As soon as the match goes in, it is extinguished. So, we need to bring some air to the party. A pump. Perfect. This should have plenty. Yes, very good. Here we go. So, I think we will add that to there. We will put our sugar in. Perfect. Maybe a bit more. Maybe a bit more. Yes, somebody say more. Okay, a bit more. Excellent. More? Oh, a bit more. Okay. Now, I sense a pattern. So, we are going to add a nice flame right here. Perfect. Tighten it up, make sure it doesn't go anywhere. And then we will push the foot pump and see if we can get a nice big fire of London. Here we go. Are we ready? 5, 4, 3, 2, 1. Oh. Delicious, but not fiery enough. Let's try again. This time, I think we need more fire. Here we go. Start here. A little bit more in. There we go. Don't you love science experiments? They always go right every time, first time, don't they? Here we go. Ready? 3, 2, 1. Oh, delicious. Let's see if we can get it going one more time. Would you like to see it again? Yeah. Excellent. Here we go. Ready? 5, 4, 3, 2, 1. Oh, lovely. And we are nice and safe. I never even had to use my baby bottle. So one last time. Would you guys like to tell me the ingredients of fire? I will do the actions and you will shout them out nice and loud. Are you ready? Yes. Ready? Perfect. Have you enjoyed yourselves? Yeah. Excellent. Well, I'm going to hand it back to Greg and to your next speaker. Thank you very much, everybody. Be safe with your fire.
Dangerous Dan, everybody.
Thank you.
Thank you, Dan. Good job, that was fun. Don't know if someone enjoyed themselves. So we've got to wait. I mean, keep going. Don't let us stop you. Favorite bit of the show so far. Thank you. I don't know whether my favorite bit, actually, Dan, was the egg in the mouth. Or oxygen. Where's the person oxygen? Great work. You got a career on the West End. That was a lot of fun. That was a good way to start the show, wasn't it? Yeah. While we all cool off, There's a few people. No, you've got eyebrows and everyone was in one piece. We're okay. We're just going to take a little breather, reset the stage a little bit. While we do it, we're going to show you a video. It's going to be up on the screen. It's from a series from the IET YouTube channel, which is worth checking out. This is where young people meet awesome engineers around the world. And we're going to meet 14-year-old Sahia who meets engineer John in Brighton. Here we go.
Hi guys, my name's Sahib Patel, I'm 14 years old and I'm here today in Brighton to see the British Airways i360 building. Today we're going to be talking to John Roberts and really finding out about engineering as a topic and as a job opportunity to see if it's something that I should be taking and you at home as well. Hi John, thank you very much for seeing me today.
Hello.
We're here at the i360 building. I've already been on it, it was sensational. Before we start, I'd just like you to introduce yourself for those of us out there that don't really know who you are.
Right, my name's John Roberts. I'm the Chief Engineer for the Brighton i360 project, which is now called the British Airways i360.
Who inspired you to create all these things?
I actually really started because I worked on building sites when I was at school, and the real thing that then inspired me to be an engineer is I was working away 7 days a week doing physical work on a construction site, and then just very occasionally the engineer would come and make a visit to the site. And I thought, you know, I want to be like him when I leave school. So that is actually what made me decide to go to university to become an engineer.
If you could sum up your career in three words, how would you sum up your career?
Different every day, there's 3 words. I mean, literally, I do different things every day. And there aren't that many careers where you can say that.
So John, how come engineering isn't such a well-known job?
We need to tell people examples of projects like this, where you can see engineering in front of your eyes is a really good starting point.
Definitely. Inspiration to all of us. Thank you.
I've been on that i360. It's very cool. Great engineering, I tell you. And how good was John? So that was a little flavour. The view from the top of that is amazing. If you want to see the world from even higher, what are our options? Well, you could go up in a plane. Yes, of course you could. How about sending up a spacecraft? That sounds fun. Great segue, Greg, because our next speaker is an awesome engineer who does exactly that. Please, show me your hands. Clap those hands together. Make some noise for the IET's Young Woman Engineer of the Year, Kira McGraw!
Thank you very much. Hello, everyone. My name is Kira, and I am a lecturer in aerospace engineering at the University of Manchester, and I design space missions. So today, I am going to take you all on a whirlwind tour of the life and death of a satellite. And to help me do that, I have here with me today my trusty satellite. Oh, he's backwards. That won't help. Let's turn him around so you can see his face. There we are. So this is a perfect replica of the University of Manchester's very own satellite, SOAR. Now, SOAR was launched into orbit in the summer of last year. It carried out its mission for about 9 months, and then earlier this year, it ended its mission and came to the end of its life. Now, when I say this is a perfect replica of the satellite, it is exactly the same size as the satellite that we sent into orbit. It was really this tiny, about the size of a shoebox. Now, SOAR, when it went into orbit, it was about 400 kilometers above the Earth. That's about the same distance as from here to Scotland. And I actually travelled down from Scotland yesterday on the train. So when you think about it, it's not very far at all. And what that makes me ask is, if the satellite is this small, and if it only needs to go to Scotland, why is it so hard to get things into space? Why do we need these big rockets with big flames coming out of them to get them into space? And the trick is that it's not actually all that hard to get something to go up into space, to go to that height. The trick is making sure that it won't fall back down and land on our heads. So, to explain to you what I mean, I have my trusty swing ball set with me. Has anyone played swing ball before? Yes, yes, some great hands. Excellent. Good. No. Well, hopefully you'll get to play it if we get some sunny days in the summer. It's a great game. So, the goal of swing ball is that you want to hit the ball so that it travels around in a circle around this central pole. And that's exactly what we want to do with our satellites. So when we put our satellites up into space, they don't just sit there. They travel around the Earth in a big circle that we call an orbit, just like this ball travels around this pole. So if we imagine that this ball is like our satellite, we imagine that this pole is like our Earth, and this rope represents the gravity that's always pulling everything down onto Earth and makes sure that we stand on the ground and we don't float off into space. And that gravity pulls on our spacecraft in the same way that it pulls on us. And what we want is we want our spacecraft to be traveling in these circles around our Earth. Now, what happens if we take our spacecraft and we bring it out to 400 kilometers, we bring it out to the distance of Scotland, and we just let go? It's just going to fall down, and it's going to hit the Earth. It's just going to land back down on our heads. So that's not much good. What about if we throw it really hard straight up into the air? Well, that's not much good either. It's still going to either fly off into space, or if we don't throw it hard enough, it's going to come straight back down and hit the Earth. Not what we want either. So, if we want to get this into a circle around our Earth, which direction do I need to throw it? I need to throw it this way? Yeah? Yes, exactly. I need to throw it sideways. I need to give it a push sideways, and I need to give it enough speed that it can travel around without falling down. And that is exactly what we do with our spacecraft. So when we put SOAR onto its rocket and send it up into space, the rocket's job is not really to get it up that high. The rocket's job is to turn over sideways and give it a big push to the side to make it go fast enough that it won't fall straight back down to Earth. And here's a number that you can take away with you and tell to your friends. There's this magic number that we need that satellite to go at, the magic speed that we need it to go. And that speed is 7 kilometers per second. And at that speed, we could get from here to Scotland in less than a minute. So that is incredibly fast. And so when SOAR was in orbit, it's traveling in this giant circle around our Earth at 7 kilometers a second. That means it travels around that whole circle in just an hour and a half. And while it's traveling around in this big circle, the Earth is spinning underneath it, and it's passing over every single place on the planet. But what happens after it's 9 months, when it's finished its mission? What happens then? There's a few different things that can happen with spacecraft at the end of their lives. But I'm going to tell you about what happened to SOAR and what happens to a lot of spacecraft when they finish their missions. And we do say the end of their lives because we get very attached to our spacecraft. So at the end of their mission, the satellites, we stop looking after them quite so much. We stop maintaining their orbit, is what we call it, and something happens. You'll have seen it when I was throwing this ball around. If I let it go for long enough, it won't go forever. It'll eventually start to slow down, spiral in towards the pole, and eventually hit it. Now, why is that happening? The reason it's happening is because of this rope. This rope is rubbing. It's rubbing on this post, and that's causing something called friction. Has anyone ever heard of friction before? Yeah. So it's causing a rubbing. If you put your hands together and you try and slide them past each other and you've pressed them really hard, it's really hard. And that friction causes the ball to slow down. Now, SOAR was not attached to a rope when he was in space, but what was causing friction in space was air. There's not enough air in space for us to breathe, but there is a little bit up there where our spacecraft are. And those little bits of air, when we're traveling at 7 kilometers a second, those little bits of air crash into the front of the spacecraft, they rub along the side of it, and they slow it down. And when it slows down, it's not traveling at that magic number of 7 kilometers a second anymore. And so instead of carrying on in its circle around the pole, it starts to slow down and move closer to the Earth. And the closer to the Earth that it gets, the more air that there is. And so the more that it slows down and the closer it gets to the Earth. And eventually, there is so much air that something else happens. Because there's something else that friction can do. Friction doesn't just slow things down, it also heats things up. So if you put your hands together in front of you and you rub them together really fast, really fast, you'll feel that they'll start to warm up. And you can imagine this is the kind of thing you might do on a cold winter's day if you forgot to bring your gloves along. And that's what happens to our spacecraft. It experiences so much friction that it starts to heat up. Now, like we heard from Dangerous Dan, there's not enough oxygen up there for it to catch fire, but eventually it will get so hot that it starts to melt. It starts to vaporize, and eventually it will burn up in the atmosphere. Now, the question I always get asked is, if that's what happens to our spacecraft, what about our astronauts? How do we get our astronauts safely back from the space station? Because we don't want them to burn up in the atmosphere. So we have very clever engineers who have built things called heat shields, which we use to protect our astronauts when they're coming back from space. So in the little capsules that they sit in, they're protected by a shield, which stops them from heating up and burning up. So the heat shields that we build for our spacecraft are a lot more sophisticated than the one that I have built for this balloon. But what I want to show you is that using really simple materials and our knowledge of science, we can engineer a solution ourselves. And if you want, I challenge you to try this at home with some help from your parents or your guardians and see if you can make a better heat shield than I have. So this is a really simple one. I've got some cotton wool, I've got some foam, and I've got some tin foil. The kind of tin foil you might put on a chicken in the oven to make sure that it doesn't burn. And this is going to be my heat shield for my balloon. And we're going to see if we can get the astronauts safely back from space using this heat shield. So I'm going to count it as a success if we can make this balloon survive for 10 seconds without bursting. Do you think I can do it? No? To be honest, I'm a bit dubious as well. That's a fair question. Somebody believes in me down here, which is excellent. All right, so I want you all to count along with me. And as engineers, we have to test our hypothesis. We have to check that what we've made is going to work. So this is what we're going to do. So when we start the flame, I want you all to count with me from 1 all the way up to 10, and we'll see if our astronauts can survive. Are you ready? Yes? Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey! Thank you all so very much for coming along today. My name is Kira. It's been amazing to see you all. I hope you've learned something. I hope you found it exciting. And I hope you're excited about space. Before I leave, the last thing I want to say is if you are excited about space, I guarantee you there is a job in space for you in the future. Thank you very much.
Thank you so much, Kira. Kira, everybody! See how exciting engineering jobs can be? So next up, it's going to be my turn to stand up here and tell you about a STEM, science, technology, engineering, and maths adventure that I went on. But again, so I can move some stuff off the stage, we're going to have another video from the Awesome Engineer videos. And this is when 12-year-old Iona met engineer Roma on the Millennium Bridge. Here it is.
Hi, I'm Iona, I'm 12, and today I'm here to find out a bit more about structural engineering from Roma Agrawal. You're a structural engineer. What does that actually mean? What do you do?
So my job is basically to make sure that structures stand up.
Okay.
So we're standing on this bridge, for example, and a structural engineer has done some maths and some physics to make sure that this bridge is safe, so that when you walk over it, it doesn't kind of collapse and send you straight into the Thames.
So what made you want to become an engineer?
So I always liked maths and science at school, and one summer I actually had a work placement where I had this really boring job, but all the people sitting around me were engineers. And they were designing the equipment that the physicists use to detect particles like the Higgs boson, which was incredible. And I thought, right, this is what I want to do.
So why are we on this bridge in particular?
So this bridge is quite an interesting bridge. So it was built in the year 2000 and it's called the Millennium Bridge, but it also had a slightly funny nickname, which was the Wobbly Bridge. And the reason it got that nickname was because when it first opened and people started walking across it, it started to wobble from side to side a little bit. And what I've got to show you is a demonstration involving jelly babies to explain how the different ways are that bridges can actually vibrate. So this is the infamous Jelly Baby Bridge, and I can assure you that many jelly babies were harmed in the creation of this structure. So the reason some bridges wobble is because of an effect called resonance. So what can happen, for example, is if you are a big band of soldiers walking down a bridge, you're all stepping and marching in step, and what can happen is you start to resonate the bridge so that it starts swinging like this. Or you might, like on the Millennium Bridge, make it move side to side. And when that started happening, because the bridge was moving from side to side, people started stepping in exactly the same frequency as this bridge was moving. And then the third one is also when you get the wind blowing onto a bridge and you get it resonating in a different way, like this, kind of twisting up and down. And these effects are not very good for bridges because it basically makes them crack or move or makes you feel unsafe. So we have to, as engineers, make sure that these kind of things don't happen.
So thank you so much for telling me all this. I've definitely learned a lot about engineering and I will consider it in the future.
That's fantastic, Iona. You're very, very welcome.
Just want jelly babies now. How cool is that jelly baby bridge thing? That's really fun. They're very hard to make. I've tried one. It took many, many hours. Right, it's my turn to tell you about a STEM adventure now. And this one uses a lot of engineering. So I am a scientist by training. I'm also a science journalist doing stuff on TV and YouTube and radio. But I am also a bathinaut. Thank you for the two of you who went, ooh, and the one who went, what? Okay. What on earth is a bathinaut? Good question. Do we all know what an astronaut is? Have we heard of the word astronaut? Good. Okay, good. Let's break down that word and see where it comes from. So we can look at the first bit's astro. That comes from the Greek astron, meaning star. The second bit is naut. Come back. Where's my screen gone? Am I going to do this without slides? Is that my laptop that's turned off? Ah, sad times. Can we try to fix it? Oh, that noise is my laptop not happy, isn't it? Good, let's see what happens. Right, so astronaut. Astron comes from stars. Naut comes from the Greek nautes for voyager. So an astronaut is someone who voyages through the stars, which I think is really poetic. Bathinaut, bathy, comes from the Greek for the word deep. It's back. Deep. So a bathinaut is someone who voyages through the deep. So I got to go and voyage through the deep, dark ocean. This is actually a photo of me. That's me. If you go to the deep, dark ocean, don't wear a deep, dark coloured top. Because then any cool photos that you get, you can't actually see yourself. Shucks. I wasn't too happy about that. But don't worry, I'm going to show you some videos of this dive down to the bottom. And I want to tell you about the amazing engineering that allowed me to travel into the deep, dark ocean. But first, let me introduce you to two people, the first ever bathinauts. William Beebe on the left. He is a naturalist like Sir David Attenborough. He wants to look out into the world and look at the wildlife that's out there. No one has been down into the deep, dark ocean and looked at the life down there. And he got friends with a guy called Barton, Otis Barton. He's an engineer. And Beebe challenged Barton to make something to take them down into the deep ocean. How are they going to do it? Well, first, there's a problem to solve. You look at the other ways that people have solved the problem. So first you look at a submarine. Submarines have been designed. Submarines have gone down to a depth of 117 meters, which is 1 and a bit Big Bens. So you think how high a Big Ben and then a bit of Big Ben would be down in the water. That's how far down a submarine had got. Great, but Beebe wants to look out at the ocean. There are no windows in submarines. So, what else could they do? Okay, well, they could look at an armored suit. These things are amazing. These are suits that people would pull on and they'd go down into the ocean. But they're a little bit clunky. They do go a bit deeper, though, down to 160 meters. What's that? Almost 2 Big Bens. They wanted to go deeper. They wanted to go together. So what did they come up with? Well, Barton designed this. It's called a bathysphere, a sphere that goes into the deep. This is great because it's actually got windows, although the windows are only about the size of my hand. You can see 2 of them. They're at the back. They're through the hatch because that's the hatch that they crawl in through to get inside. And then the hatch is put on top and it's closed and they're inside the bathysphere. And you see that cable going up the top? That's attached to a ship and they are splashed into the water and they go deeper and deeper. And there's another cable going off to the right-hand side there. That cable, what that does is it has 2 things. It has a telephone line going up to the ship so they can actually talk to the ship up at the top. Hi guys, we're okay. Yeah, we're good. What have we seen? A fish. And then the other thing is they've also got a light. They've got a power line to a light and they hold the light against a window and they put their face against the other window and they wait until something swims past. How far did they go down? Well, the deepest that they got to was 245 meters. 2.5 Big Bens, but I want you to remember that number, 245 meters. And where did they do it? Where was the place that the first ever bathonauts dived? Here. Where is here, Greg? This is Bermuda. This is the island of Bermuda. And if you go onto Google Maps and you type in Bermuda, you see Bermuda. And you're like, okay, you zoom out and there's just more water. You zoom out again, and okay, we're getting a bit of a sense of it now. About 700 and a bit miles from New York, 1,000 and a bit miles from Florida, 3,000 and a bit miles from Cornwall. So that's where Bermuda is, okay? Why did they dive off the coast of Bermuda? Well, this is a cool animation. There's the top of the island, but if we peel off the top of the water and look underneath the water, you can see this. These are underwater volcanoes. They formed 33 million years ago. This blows my mind. We don't call them underwater volcanoes, we call them seamounts, like underwater mountains, seamounts. And what was amazing is this is where I went to dive as well. So I went to the same place that the first ever bathonauts had dived. Super cool. This was my home for a month. This is the ship, the Baseline Explorer. And I was on that for a month, eating, sleeping, doing science research. And I dived in these. You're looking down on top of 2 submersibles. This is them, each one of them worth about $2 million, each one. And that's before you add all the science kit. They are amazing bits of engineering, these submersibles, and I want to tell you a little bit about them. But let's get ready to dive, shall we? Oh, I'm excited. Let's get down there. Hello, sir. Can I come in? Oh, it is a bit small, isn't it? All right. See you topside.
Yeah, I think we're ready to slide you into position.
Oh, we're flying. Yeah, let's turn this on. On that side, is it? We're in. I guess we're ready to go then. Yeah, good, thank you. Oh, it's so good to be in here. I've been waiting for this for such a long
Fantastic.
time.
So they're starting to release straps now. And they go, Roger that, doing a thruster. So I'm going to test my thrusters.
There's Kenny. Kenny's the swimmer. Oh, look, that's my first glimpse
of underwater.
That is my first glimpse of the underwater.
You're off the hook, and good luck on your journey to the deep.
Roger that. Here we go.
Thank you, Jeremy. We're in the water. We're on the surface of the water. We're ready to dive. What happens next? Well, right now, we are floating. When something floats, we say that it is buoyant. Now, we need to play with our buoyancy today in order to sink into the water and to come back up again. And this submersible is an awesome bit of engineering that is designed to help us do exactly that. So how does it do it? Well, it uses these tanks at the side that are called the main ballast tanks. And I want you lot to have an idea of what we can do. So let me show you a schematic, right? So here's a diagram of it. You can see how big those main ballast tanks are. They're currently full of air. What should we do so that we can start to sink? Yell it out. Let the air out. Nice. What should I replace the air with? Water. Genius. We're surrounded by it. We're going to open the vents at the top of the main ballast tanks. The air that's inside, that's keeping us nice and buoyant, is going to come out. Water's going to go in the bottom. We're going to get much heavier, and we're going to start to sink. Should we dive? Rubbish. Should we dive? Let's dive.
You're clear to vent and dip down a little bit.
Roger that. Opening vents now.
Okay, so tell me what happens as we open the vents.
So you can see the air starting to come out there.
Yep.
Right? And it's going to tip forward. And then it's going to roll back in a minute. So that's our start.
That's quite a scary feeling, actually, isn't it?
Yep.
Sub on the way down. Have a look at what's changing in the world around us.
Topside, topside. This is Nomad. My depth is 24 feet. My heading is 240. My life support is okay, and my vents are secured.
So we just hover here for a little bit?
No, we're still going down.
Oh, we're going down?
Yeah, yeah.
You just can't tell at all?
No. So we're sinking.
Is that a co-pilot job, just to clean the windows?
Absolutely.
I can do that.
Yeah. Yeah, there they are.
That is a phenomenal sight. It's like they're flying.
They are.
Isn't it?
Yep.
Whoa! Yeah, hi guys, we see you. Brings it all back. Such an amazing thing to do. So what did you see change in the world as we started sinking deeper? What did you see? Again, shout it out. It got darker. Yes, there was more water, but yes, it got darker. Yes, well spotted you lot. We can explain that really easily. So water scatters light. So the further and further we go down, the more light has been scattered by the water. That is why it's getting darker. And in fact, this is a sped up video as we're going down, 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 down. You can see it's going to get darker and darker and darker. For the science nerds in the room, it's also going to get bluer and bluer. And that's because water absorbs the different colors of light, red first and then green. So you're left with a world of blue. So you end up in a dark blue world. Now, we start up in the sunlight zone where there's lots of light, lots of life. And then we go down into the next area, which is called the dum-dum-dum twilight zone. And as we go down into the twilight zone, it gets a lot darker. But also, it's quite a hard place to be because there's a lot of water above us and around us, and that water's heavy, and it's squashing the sub. And the sub actually gets squashed, so much so that when we're at 200 meters down, which is where we are right now, in the twilight zone, it's like having an aeroplane sat on top of the sub. So how does it survive? Well, I asked that question to Kelvin. Tell me about this incredible machine. How can it survive those massive pressures?
Well, we're in a perfect sphere. So this is an acrylic sphere, and it is built to handle that pressure. So if it was square, the sides would push in, but because it's a perfect sphere, it doesn't crush. It pushes in on itself and actually gets quite strong.
It clearly got very dark. We lost my laptop again. But all he was saying was, because of the shape of it, very clever engineering, it gets squashed in all directions when it's a sphere. The same reason that Barton came up with the suggestion of a sphere again. Oh, we're back. There we are. Okay, nice. So we're there, we're sinking, we're down at 200 meters-ish. We're trying to get to what? Remember that number I asked you to remember? Good work, 245 meters. That is the place that those first ever Bathonauts dived to 90 years ago off the coast of Bermuda. Same place I was going, and we're about to hit it. And when we do, something happens. Oh my word, what's that?
That's the wall right there.
Oh my word, this is phenomenal.
Topside, topside. This is Nomad. My depth is 832 feet. My life support is okay, and I'm with Nemo.
So we've been traveling through this dark, dark space, and suddenly we see that. What is that? Well, that is the side of one of those underwater volcanoes that formed 33 million years ago, right? That is the side of one of these seamounts. We've reached our destination. And when we're there, we then spend our time going around that seamount doing science. We're taking videos, we're collecting samples, we're looking at the life out in front of us. Here you can see some spiraling wire coral, big lumps of rock that have tumbled down, a few fish kind of swimming around, although this is a lionfish, we don't like them. And also, moray eel.
Oh, moray eel. Green moray.
Check that out, look, a green moray eel. this far down. That's amazing. Wow. So, that's it. We've done it. We've made it to that same depth that BB and Barton made it to. Super cool experience. We need to get back up again. How do we do that? Well, again, we play with our buoyancy. This time, remember, they're full of water, so we should let some of the water out and instead put in some air. And we've carried that with us. Compressed air down below us there. Also some oxygen, kind of helpful to be able to breathe. That's also down there in some tanks. So we slowly put some air into the tanks and slowly rise back up again. We get up to the top, and that is the end of my bit of the adventure. And then the scientists have to crunch all the data and look at everything. So that's where I'm going to end the story today. I hope you enjoyed going on that very short little adventure, that dive into the depths. And it showed you how amazing the engineering can be and the places that it can take us to. That is how I became a bathonaut. Thank you very much. Now then, coming up next is the end of the show engineering game, which I'm very excited about. We're going to get a bit silly up on stage with a few volunteers. Before I do that, though, so I can set up, we're going to watch one final video. This is when Lorenzo, Madeline, and Joshua interviewed some more awesome engineers about what they get up to in their jobs. Here it is.
What do you do?
I fix an airplane called a tornado.
I'm actually a biomedical engineer.
I work on some very special planes that go all the way into space.
Did you always want to be an engineer?
Yeah, I think I did. I was like you. I used to take things apart.
This is what I built. We call it the Neuro Ball.
What did you want to be when you were little?
I wanted to be an astronaut. Yeah, so I wanted to go into space, and I still do. I still want to go.
Does Superman fly faster than your jet?
Superman? Now then, I think he flies faster than airplanes.
How do you go to the toilet
How do you go to the toilet? So, when you're going to space, they actually put you in a nappy. Whereas when you're up in space, you float around, don't you? So you have to actually strap yourself down to the toilet. You can't have a shower either, so it's a bit smelly up there.
I am not going to space.
Feels kind of soft and kind of hard. What made you think of something like that?
My uncle had a stroke. He was not able to move his arm, and that was really sad for me. He is actually getting better. Would you buy one?
If I had a stroke.
Hopefully, that's not going to happen.
How could I be an engineer?
You basically need to find a problem that you really want to solve.
Why is engineering exciting?
Because we get to build some amazing things. So you know when you see a plane in the sky and it flies across, and engineers made that? Yeah, I know, and that's what engineers get to do.
Should we salute them? Yeah, great. Yeah.
High five.
Love that. Super cute. Thank you so much, Lorenzo and Madeline and Joshua, for that. I love how that shows how varied different careers are in engineering, right? You've got someone helping someone who had a stroke, someone sending planes up into space. I loved Gillum as well there, said that all engineering is finding a problem and then finding a way to solve it. So anyone here can be an engineer, right? You, all of you, everyone watching at home. Anyone can be an engineer. You just come up with a problem and you find a way to solve it. Should we have a quick fun game just to end us off? We've got like 5 minutes left. Okay, I want to show you something you can try at home, something that you can engineer at home for yourself. It's one of my favorites. It's a ping pong cannon. Didn't hit anyone? Good. Phew, health and safety. Right, so this is how you make one of these. You get yourself a paper cup like this, and then all you need to do is on the small end, you need to either push it with your thumb or use some scissors to carefully cut around it, rip the bits out so you end up with a gap, right? So you've just got a hole in the bottom. Then you take a balloon and you tie a knot in the top of the balloon, in the neck of the balloon, which is a bit weird because you haven't blown it up, but you see what I mean. So then there's a hole at the bottom, and then you get some scissors, you get grown up with some scissors, and you carefully chop the end off the top of the balloon. So what you end up with is a balloon tied at the neck, but chopped off a bit at the top. And then you stretch this over the top of the cup, like so. You take some tape, you tape around it, easy as that. You've got yourself a ping pong cannon, right? And then to fire it, all you do is you pop your ping pong in, you use the stretch of the balloon, fires out the, oh, so close, almost on the head. fire out a ping pong like that. So this is what I thought we'd do for a bit of fun for a few minutes. I want 3 volunteers. Hang on, you don't know what you're volunteering for. I'm going to have 3 volunteers who are going to come up here and we're going to have a little bit of fun with the ping pong cannons. Can I have 3 volunteers? Hands up if you'd like to come up. All right, so I need to make sure I don't pick the same people as Dan picked. Got to try to remember who that was. So I'm going to have one person from the back. I'm going to have one from the front, one from the middle, one from the side. So I'll have you. Hello. Yes, you. Yes, me. What, me? Yeah, hi. I'll have you there at the back. Hello, come up. Yes, you. Yes, me. What? And I will have, so there's one there. I'll have you. Come on up. Come up to the stage, come up the sides, that's it, you're perfect. Come up there, round the corner, wiggle around the back, come on up. Give them a round of applause as they come up onto the stage. Hiya. Come on over this side. Keep coming up. Now, you're going to stand behind one of these buckets each, facing me. Okay. You've got some ping pong cannons down there on the side. You see them? We can unthread them. So you've got one there, So there's one for you to start with. There's one for you. If they break, these are spares. That's my thinking, right? And then you've got yourself some ping pong balls inside these bins. We've numbered them. So these are number 1, number 2, number 3. You're going to take them out, load one at a time, and then you're going to fire one at a time. So we go fire, 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 right? And you're aiming at me. Okay. So we're going to just fire all of our ping pong balls. It's precision. This is what we're looking for here, right? Good luck. Can't aim these things. And you're going to try to get as many as you possibly can in the bin. And we're going to see who comes out on top. It's just a bit of fun with engineering. Are you up for the challenge? Yes. Yes, okay. All right, you ready? So you're going to be first. Let's count them in. Maybe we have some music with this. That'll make it fun. 3, 2, 1. Okay. I'm going to start close, all right? Are you selecting? It's not Wimbledon. You don't need to select. They're all the same. Just grab it. There it is. Grab a ball. Put it in. Have fire. Oh, it's fallen out the end. Person number 2. See, it's all a learning process. Oh, I'm not going to count it because it bounced. Next one. Look at me sticking to rules. Are there rules? I don't know. Oh, that's my bad. Right, I'll stay close. Let's go again. Yes! First one's in. Good job. Whoa! It's in. It's off the knuckles. We'll count that one. Next one. Okay, let's speed this up. Not yet. Okay, I'm going to go back another step. Go for it. Pull it harder. Yes! Good shot. Next one. Whoa! Nice. Oh no! Have another go. Quick, we'll edit that one out. No one saw it. It's definitely not live. Oh no, not that one though. Here we go. Good job. Nice. That's the one. Okay, I'm going right back. Only got a few left. Go for it. Disaster. Okay. Oh no. Swap to a different one if you want, if it's got a bit crooked. Good work. Last ones. Tell you what, I'm tired. Great. Oh, that was my bad. Sorry. Oh, no. Yes. Have you got any more? You're out. Last one. Try one more. Quick, big crescendo. Oh. Whew. Give them a huge round of applause. Okay. Let's see who got the most out. 1 for you. 2 for you. Oh, 3 for you. 1 for you. 2 for you. Another 1 for you. I can't keep these counting. Another 1 for you. That's 3. What's that? That's another one. That's 4 for you. I've got 2 more 2s. So hang on. How many of you, did you all get the same? 3, 4, 4. Round of applause. You all smashed it. Give them a round of applause. You can all go back to your seats. Thanks for coming and having a bit of fun with me on stage. That was a lot of fun. You can just leave them on the floor. I'll deal with all that afterwards. It's a fun mess. Give them a huge round of applause. They're not off the stage yet. Go wild. You're free. Go wild. There's another fun game that you can do using the stretch of a balloon, which is when you cut off the neck bit of a balloon and you stretch it over a can and you make bounce pads. Love these. This was a game that we came up with called Let's Go Bounce. And actually in the Marconi room, there's different exhibits and you can go and try this one and they just bounce off the top like that. And your challenge is to launch them down a tube and see how many you can bounce them off. Have fun with that in the Marconi room afterwards. I have to finish now. Because look at that, bang on time, 11:30. Have you all enjoyed the show? Yeah. That was good, but I think we can do even better. Have you all enjoyed the show? Brilliant. Just remember that all you need to do to be an engineer is spot a problem and come up with a solution. And as I said, every single one of you here in the room and everyone watching live at home, you can be an engineer. You really can. All these jobs, anyone can do these jobs. Thank you very much for joining me. Thank you very much to everyone here at the IET. Thank you for everyone watching online. Thank you to my guests, Dangerous Dan and Kira McGrath. Thank you to you lot for coming. Please enjoy the rest of your day out there. For more on the wonderful world of engineering and technology, check out the IET's Engineer a Better World website. There's loads of things on there that you can go and check out. That is pretty much it. Oh, there's a new competition launching soon where you can design a backpack of the future. So that will be a lot of fun. Check that out. Enjoy the rest of Engineering Open House Day. My name's Greg. Thanks very much. Bye!
There's no air left to breathe. Do you just wanna to be left outside the grid? It's all for sure, you didn't know. I wonder what it meant to be. If I let go and let it flow, I think there's more to see. I just need a break. I'll take what you think. I just need to break. I'll take you to a trip to the other side. I'll take you to a trip to the other side. Take a trip to the other side. I'll take you to a trip to the other side. Take a trip to the other side. I'll take you to a trip to the other side. Take a trip to the other side. I'll take you to a trip to the other side.
it. That's what I'm talking about.
Wait! Okay, now, from the beginning.
Hit it, boys.
This place, that'll rock this place, that'll rock this place, rock this place, rock this place, rock this
From the beginning. This place, that'll rock this place, that'll rock this place, rock this place, rock this place, rock this
So now you're here again, knocking at my door. A little too late for, I'm sorry for. The lights went out 'cause you kept cutting the cord, and I started to fade into your gray. See, I finally opened up my eyes, and I saw me coming back to life. That I'd be better without you inside. It's time to be someone I wanna recognize. The future starts right now. I made a reservation, but you never came, so I'm checking out. The fire you stole away, I know one day we'll come back around. The future is now. I waited for you in the passenger seat. There's only so far I can ride in your dreams. While you were chasing everything else but me, I'm starting to break out from your gray. See, I finally opened up my eyes, and I saw me coming back to life. That I'd be better without you inside. It's time to be someone I wanna recognize. The future starts right now. I made a reservation, but you never came, so I'm checking out. The fire you stole away, I know one day we'll come back around. The future is now. Backing down, 'cause the future is now. Not backing down, 'cause the future is now.
There you go again, looking so handsome. Oh, you have your way, and it's making me weaken. You and your stylist, walking like that. It's really getting too much, but I can't pull back. Though I try to resist, I can't fight this. And no one makes me feel like you do. And no one sets my body on fire. And no one gives me shivers like you. Oh, no one does it better. How I try to sleep, but you're deep in my mind. Got a hold of me. When I'm awake, I'm all blind. You and your magic, like infinite power. God knows I try to resist, but you're pulling me closer. Oh, I gotta stay away, but you won't let me. No one makes me feel like you do. And no one sets my body on fire. And no one gives me shivers like you. Oh, no one does it better.
Jack. You sure you can handle? We be faster than Django.
Please put your hands together for your host, Greg Foot.
How are we? Are we good? That's not bad. I'll give you a 5 out of 10. Are we good? Yeah! That's better. How lovely to see you all here back in Savoy Place. This is great. It's so great to see all your faces. Hello. Also, you all need to turn around and wave at the cameras there because there are lots of people watching online. Wave at the cameras at the back. Hello. Hello, hello. Welcome to the IET's Engineering Open House Day. But what's that? So what that is it's a big old celebration of science, technology, engineering, and maths. STEM, STEM. That's why you might sometimes hear this word STEM. And what we want to do today is we want to introduce you to the awesome world of science, technology, engineering, and maths, and the really varied loads of careers that you can find in STEM. Everything from, I don't know, Formula One cars. That's kind of fun engineering. Getting a rocket up into space. That's kind of cool engineering. Saving people's lives, helping the health of the planet. There are so many varied, exciting, creative jobs in science, technology, engineering, and maths. And anyone in this room can do it. Trust me, you. Even you, sir. You. Everyone in this room and everyone watching at home, you can be an engineer in one of these really fun areas of jobs. Or you could be a technologist working with cutting-edge technology. In fact, let's try this. What would be your dream STEM job? And this is for everyone, small people and big people in the room. Think of it, turn to the person next to you, and tell them what your dream STEM job would be. And this is the same for anyone watching online as well. I'll give you a few seconds. I can hear some great suggestions. All right. Keep them coming. Keep dreaming them up during the show. Dream them up during the show. I'm very excited about what you lot are going to be doing in the future. What are you going to be doing in the near future, i.e. the next hour? Well, let me tell you. Coming up, things are going to get hot when Dangerous Dan takes to the stage and shows you the fundamentals of fire. We're going to be, there's a few people. We're going to be joined by Kira McGrath. Kira is the Young Woman Engineer of the Year, no less. And she's going to be telling us, She's going to be telling us all about spacecraft, right? How to get them up there, how to launch them, what they do, how to get them back down again. Plus, she's actually brought along a spacecraft for us. You might be able to see it if you look carefully on the stage. You might be able to see the spacecraft right now. What else are we going to do? You're going to hear and meet a whole bunch of other awesome engineers. I am going to tell you about a STEM adventure that I went on myself, diving down into the deep, dark ocean. Looking forward to giving you a little short version of that later. And then at the end of the show, I want to play a little silly game on stage with a few of you. Think some of you might be up for that? Okay, all right. Loads of other stuff going on here at Savoy Place as part of open-earing. That's the other day. Engineering Open House Day. Outside in the Marconi room, if you haven't been there yet. Go out there, take some photos, grown-ups, put them on social media, use hashtag IET Open House on the bottom right-hand corner there if you can just about see it, because we want to see what you've been up to. Right, shall we get this show started? That was pretty good, but we'll do it once more. Shall we get this show started? Show me your hands, clap them together, make some noise for Dangerous Dan!
Hello everyone, good afternoon. My name is Dangerous Dan. I am going to be doing your mad science for the next 15 minutes. So, by show of hands, who here has done mad science before? Excellent. Loads and loads and loads of you. Good. Well, today we've got a very exciting one. We are going to be doing the fundamentals of fire. So I have a nice easy question for you. What are the 3 ingredients of fire? Who can tell me one of the ingredients? Yes. Heat. Fantastic. Come on up. Would you like to join me on stage and be heat? Yes. There is no such thing as a cold fire. You must have heat. Come and stand here. So, when I say heat, you are going to do this. Like your feet are on fire. Are you ready? Heat. Excellent. 1 ingredient down. Yes, round of applause. Fantastic work. What are the other ingredients for fire? I'm looking around. Who can I see? Yes, right there. Liquid nitrogen? Unfortunately, that is not one of the ingredients for fire, and it's very, very cold. Yes. Oxygen, fantastic. Come up here. Oxygen, round of applause for that. Very good. Oxygen. Take a deep breath in. Delicious oxygen. 20% of our atmosphere is oxygen, and it is completely necessary for fire. Cannot have fire without it. It's like trying to have a fire in space without oxygen. So you stand here, oxygen, and when I say oxygen, you're going to do this. Oxygen. Are you ready? Oxygen. Look at that. Fantastic. We have oxygen, we have heat, we have warm breath, but we do not have fire. We need one more thing, one very important thing. Yes. Amazing. Fantastic. Fuel. Would you like to come up and join me and be fuel? Fuel is the category of all of the things that burn. Something like paper and matches and oil. All of these things, if they catch fire, they are fuel. And you are my fuel. You're going to stand here like this, and when I say fuel, you're going to do this. Fuel. Fuel. Very good. Fantastic. Right, so these are our 3 ingredients for fire. You are going to remember them, and when I place my hand above their head, they are going to do the actions, and you are going to shout out which one they are. Are you ready? Louder! Oh, who said oxygen? Very good. Now, these are our 3 ingredients. If you don't have all 3, you don't have a fire. If we take away our lovely oxygen and we only have fuel and heat, do we have a fire? No. This is kind of everything in this room that is a little bit hot and a little bit fuel. Luckily, we don't have oxygen. We have plenty of oxygen. Luckily, this would be like having a fire in space. You need the oxygen. If we take away our lovely fuel and all you have is oxygen and heat, we've already established this is just warm breath. And if we take away our lovely, which one are you? Heat, and we have fuel and we have oxygen, do we have a fire? No, good, because that's everything in here. So, I think a round of applause for our 3 volunteers, our 3 answer correct. Well done, well done. Thank you very much, guys. You've been brilliant. We talked a lot about fire, so I think it's time we set one up. I've got my lovely candelabra here. Look at this. Do you feel it getting more romantic in here? Lovely candelabra, perfect. Now, obviously fire is incredibly dangerous, so we need to do a little bit of fire safety beforehand. I am going to bring on a fire extinguisher. This is my lovely drinking bottle from home. We are going to fill it full of a little bit of water, so we are nice and safe. Here we go. Perfect. Now we've got our fire extinguisher full. How am I going to put out my flames? Anybody have any idea how to get the water from here to there? Yes. Squeeze it. It is a solid bottle. Unfortunately, it cannot be squeezed. Something else. Pour it. Unfortunately, my arms are not that long. I want to be really far away from the fire when I put it out. Yes. Move a bit closer to the fire. No, don't move closer to the fire. Yes. Throw it. What if there's 2 fires? I've only got 1 bottle. Half and half. Yes. Splash it over, that's quite good, but there's a really, really easy answer. Yes? Unscrew it. And then pour it. No, no, no. That's not going to work. There's something else. I can move the bottle in a certain way. Yes? Levitate it? Goodness me. No. The answer is quite obvious. All I need to do is shake the bottle. Do you believe me? Shall we have a look? Ah, that definitely works. Look at this. No, it's working perfectly. There we go. There we go. Let's see if we can put it out. Excellent. All the way over here, we managed to put our fire out with our bottle. Now I'm nice and safe. I can have another go if I really want to. And you guys are nice and wet. So, does anybody know the science of this? It is quite simple, really. Inside this bottle, it is not normal water. It is, in fact, carbonated water or sparkling water or fizzy water. All that fizziness is actually carbon dioxide bubbles, which you can see rising to the top. When we shake the bottle, those carbon dioxide bubbles rise much, much quicker and then expand. That gas expands, creates enough pressure to push the water out of the top, and then the water extinguishes my fire by removing a little bit of the heat. Very, very simple. So now we are nice and safe. I think we should do a fiery experiment where I introduce you to a good friend of mine. This is Egbert. Say hello to Egbert. Now, Egbert's had a very large lunch, and unfortunately, he no longer fits inside his house. He's too big to get inside his front door. Does anybody have any suggestions on how I am supposed to get Egbert from here into here? Yes. Crack him? No! This is my good friend Egbert. Absolutely not. Yes. Heat the bottle from underneath. Oh, it's going to be very hot in his house. I don't think that's right. Yes. Heat it from the top. Well, you're very into heating Egbert's house, but no.
Take the egg off the top, put a lit match in, and then put the egg back.
You want me to set fire to all of the things in Egbert's house? Oh, if you couldn't fit in your house, I wouldn't set your sofa on fire. That's a terrible suggestion. Oh, the answer's obvious. We're going to give Egbert a haircut. Yes, I know you're thinking he doesn't have much hair in the first place. But if we give him a very special mad science haircut, the flaming Mohican, I think he should be all right. So here we go, 3 matches in. He's got an extra special haircut. Look at that. Doesn't he look brilliant? But it is not complete. Let's set it on fire. Perfect. Now we have Egbert's flaming hair going on. We can see if he fits inside his house. Perfect. Inside, and now all the fire is outside. No need to set the things inside his house on fire at all. And he did a nice little flip right at the end there as well. Now, the reason this worked is because of all that oxygen that we're burning. 20% of all the gas inside this bottle is oxygen. So when we burn it, we create a vacuum. That vacuum is not liked by the rest of the atmosphere. It tries to get in, and by doing so, it pushes on Egbert from all directions equally and sucks him into the bottle. I bet you're asking, Dangerous Dan, how do we get Egbert out of the bottle? Any suggestions? We don't smash his house. We're not going to heat it from the bottom or the top. We're not going to chop him in half. What could we do? Yes. Set his whole house on fire. No, I don't think that's the case. I think what we're going to do is try and reverse the experiment we did before. We took oxygen out, so now we're going to put more air in than the bottle can hold. By doing that, I'm going to blow really fast into the bottle, creating higher pressure in here than there is out here. This is going to go one of 2 ways. Either Egbert is going to fly out and end up in my mouth, or he is very slowly going to come out like this and then pop out. I think it's probably going to be the first one. Shall we have a look? Are you ready? 1, 2, 3. Brilliant. The first one. Thank you, Egbert. In and out of his house. Nice and simple. Right. I think it's time to do something dangerous. So, we're going to do our final experiment. This one is called the Great Fire of London. Who knows what year the Great Fire of London happened? Right in the middle at the back. 1966, or is a little... What was that, sorry? 1666, very good. Yes, 1666, nearly 400 years ago. Where did it happen? Don't say London. I know it's London. Where in London? Yes. Pardon? England? We're zooming even further out. Yes. Pudding Lane, very good. Pudding Lane in Thomas Farriner's bakery. It caught fire and set fire to 70% of London in the end. So there must be something inside a bakery that is particularly flammable, something that bakers use. And bear in mind, this is 1666 in London. All the houses are made of wood. All of them use fires to keep themselves warm. All of them have very hot ovens inside of them. So that's not specific to a bakery. But what is an ingredient that bakers use in bread and cakes and that kind of thing. What could it be? Flour. Very good. Round of applause. Flour is incredibly flammable. Very, very fine flour catches fire very, very easily. And we're going to use something similar, another thing that a baker uses. It's the same color. It's very fine again. Begins with an S. It's very sweet to the taste. You put it in tea, sprinkle it on cakes. It ends with a yugar. Anybody? I should see all the hands in the air by now. Yes. Sugar, yes, we are going to use sugar, and we are going to use the most dangerous of the sugars, the deadly icing sugar. Now, icing sugar is very nice and fine, which means when it goes anywhere near a flame, it should catch fire very, very quickly. Nice big spoonful. Here we go. We've got a single match. Are we ready? 3, 2, 1. Oh. Nothing happened. The sugar put my match out. Why do we think that there wasn't a big explosion? Why do you think I still have eyebrows after that experiment? What happened? Yes. No, it's not ice. It's icing sugar, but it's not ice. Yes. Very good. Inside the icing sugar is very densely packed. That means that there is no air in between and therefore no oxygen. So we need to put some oxygen in here. We had plenty of heat, we had plenty of fuel, no oxygen at all. So I brought a little bit of air with me with a pump. Perfect. We will place the pump here, tighten it up, move the candelabra, this in the middle. We will put our spoonful of sugar in. A little bit more. More? More? Okay. More? Oh, okay. There we go. Nice icing sugar in there. And then we are going to need a candle. Perfect. So, take one of these nice candles. Place it over here like this. Screw that in nice and tight so the candle doesn't go anywhere. And now, we're going to need a countdown from 5. 5, 4, 3, 2, 1. Whoa. Nice. And delicious. Would you like to see it again? Yes, so would I. So we'll light it on fire. Smelling like caramel in here now. So we will add a little bit more icing sugar. Perfect, perfect, perfect. All right. We'll add a little bit more fire to make sure this works. Second time. Are we ready? 3, 2, 1. Oh, there we go. Perfect. Excellent. So do you believe me that icing sugar is not just delicious, but also very, very dangerous? Excellent. Now, just before I leave, I am going to do the actions of the 3 elements of fire, and you are going to shout out which one I am. Are you ready? Fantastic. I hope you've enjoyed yourselves. I hope you have learned something brand new that you can take home, especially to be very, very careful with fire and icing sugar. I can hand you back to Greg. Thank you very much, guys.
Thank you, Dan. Dangerous Dan, everybody. And Egbert, of course. Let's, round of applause for Egbert, please. Egbert's happy. That was a lot of fun. Thanks, Dan. And you're right. It tastes nice up here now. Nice and sweet on the stage. Right, we're going to need to clear this mess up. So what we're going to do is going to play you a quick video. It's a video from a series on the IET's YouTube channel, which is worth checking out, where young people meet awesome engineers all over the UK. This one is going to be when 14-year-old Sahir met engineer John in Brighton.
Hi guys, my name's Sahir Patel, I'm 14 years old and I'm here today in Brighton to see the British Airways I360 building. Today we're going to be talking to John Roberts and really finding out about engineering as a topic and as a job opportunity to see if it's something that I should be taking and you at home as well. Hi John, thank you very much for seeing me today.
Hello.
We're here at the I360 building. I've already been on it, it was sensational. Before we start, I'd just like you to introduce yourself for those of us out there that don't really know who you are.
Right, my name's John Roberts. I'm the chief engineer for the Brighton I360 project, which is now called the British Airways I360.
Who inspired you to create all these things?
I actually really started because I worked on building sites when I was at school, and the real thing that then inspired me to be an engineer is I was working away 7 days a week doing physical work on a construction site, and then just very occasionally the engineer would come and make a visit to the site, and I thought, you know, I want to be like him when I leave school. So that is actually what made me decide to go to university to become an engineer.
If you could sum up your career in three words, how would you sum up your career?
Different every day, there's 3 words. I mean, literally, I do different things every day. Wow. And there aren't that many careers where you can say that.
So John, how come engineering isn't such a well-known job?
We need to tell people examples of projects like this, where you can see engineering in front of your eyes, is a really good starting point.
Definitely. Inspiration to all of us. Thank you.
Good, isn't it? Yeah. Well done, Sahir and John. I've been on the I360, actually, and it's cool. Great view from the top. I tell you, great view. If we wanted to go even higher, though, and look down at the world from even higher, how would we do that? Aeroplane, good shout. We could go on an aeroplane. Or we could use something that we send up, maybe to space, like a rocket, yes, or a spacecraft. There, spacecraft, yes. Nice segue, Greg, because my next guest is an awesome engineer who hangs out with spacecrafts. So, show me your hands. Clap those hands together. Make some noise for the IET's Young Woman Engineer of the Year, Kira McGraw!
Thank you very much. Hello. Thank you all very much. My name is Kira and I am a lecturer in aerospace systems at the University of Manchester, and I design space missions. And so today I am going to take you on a whirlwind tour of the life and death of a spacecraft. And to help me do that, I have with me here an exact replica of SOAR, which was the spacecraft that was designed at the University of Manchester. Now, SOAR launched into orbit in the summer of last year. It stayed in space for about 9 months, and then earlier this year, it finished its mission. It came to the end of its life. Now, when I say this is an exact replica, what I mean is that the SOAR spacecraft the university sent into orbit was exactly the same size as this spacecraft up here. It was really that small, about the size of a shoebox. And when SOAR went into space, it was about 400 kilometers above the Earth. That's about the distance from here to Scotland, which, when you think about it, is not actually that far. I came down on the train yesterday from Scotland in just a few hours. And so that always makes me think, if we have spacecraft that are quite so small, and they only need to get as far as Scotland, why is it so hard to put things into space? Why do we need big rockets with great flaming engines to get these spacecraft up into orbit? And the trick is that it's not actually that difficult to get something up into space. The difficult bit is making sure that it doesn't fall back down and hit us all on the heads. So, to explain to you what I mean about that, I am going to use my trusty swing ball set. Has anybody ever played swing ball? Excellent, good. If you haven't, give it a go. It's great fun, especially on a sunny summer's day. The goal of swing ball is to hit the ball so that it travels around the pole in a big circle. And just like that, when we put a spacecraft into orbit, it doesn't just sit still. It actually travels in a big circle that we call an orbit around the Earth. And so the trick is that we want to get it up into space and make it so it will travel in this circular path around the Earth. Now, if we imagine that this ball is our spacecraft, this pole in the center is our Earth, and this rope is the gravity that's pulling on our spacecraft, pulling on all of us and making sure we don't all float off the Earth, then we can use this to help us understand how we put a spacecraft into orbit. Now, if I take my spacecraft and I get it up to my 400 kilometers that I want, and I just let go, it'll just fall back down to Earth. That's not much good. If I take my spacecraft and I throw it as hard as I can away from the Earth, it'll just fall back down to Earth. That's not much good either. So if I want my spacecraft to go into a circle around the Earth, which way do I have to throw it? Yes? This way? Exactly. I have to throw it sideways. And that's what our rockets are doing when we send them up into space. Actually, what most of the rocket's fuel is used is not for getting it up into the height that we want. It's that when the rocket gets up there with its satellite on board, it tips over sideways and starts giving it a push in a sideways direction to send it into a circle around the Earth. And there's a very magic number about this. We need to make sure that the satellite is going fast enough that it'll carry on in this circle and won't fall out of the sky. And that magic number is 7 kilometers per second. Now, that is so fast that at that speed, we could get from here to Scotland in less than a minute. So when we put our SOAR spacecraft up into orbit and it's zooming around at 7 kilometers a second, it can travel the whole way around that circle around the Earth in just an hour and a half. And while SOAR was going around and around the Earth in a circle, the Earth was turning underneath it, and so SOAR could pass over every single point on the Earth throughout its lifetime in space. But what happened at the end of its mission? What happens when a spacecraft gets to the end of its life? And we do call it the end of its life because we get very attached to our spacecraft. Now, there's a few different things that can happen to spacecraft at the end of their life, but I'm going to tell you what happens to a lot of them, and this is what happened to SOAR. So you might have noticed when we were throwing our ball around in a circle, it doesn't keep going forever. Eventually, if I leave it going for long enough, you can see it will start to get slower and slower and spiral in towards the center until it eventually hits the pole. And the reason that this happens is that this rope is rubbing on this pole up here. And that rubbing is something that we call friction. Has anyone ever heard of friction? Excellent, you are experts in here. So that friction is just rubbing. It's the same thing you get if you press your hands really tightly together and try and rub them past each other. It's quite hard to do. Now, of course, in space, SOAR did not have a rope attached to it. That would have been a bit weird. But there was something else that was causing friction up in space, and that was air. There's not enough air in space for us to breathe, but there is still a little bit of air up there. And when SOAR is zooming around at 7 kilometers a second, those little bits of air were crashing into it and rubbing along its side, and that was causing friction. And that friction caused it to slow down in the same way the friction in the rope causes our ball to slow down. And as it slows down, it starts to move closer and closer towards the Earth because it can't keep up that perfect speed that we want of 7 kilometers a second. And the closer it gets to the Earth, the more air that it encounters. And the more air that there is, the more friction that it starts to feel. And so it gets closer and closer and closer to the Earth until eventually something else starts to happen. Because friction doesn't just slow things down, it also causes heat. So if you take your hands and you place them together in front of you and you rub them together really, 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 really fast, really, 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 really hard, you'll start to feel that your hands are going to warm up. And you can imagine this is the kind of thing you might do if you were standing outside on a cold day and you'd forgotten your gloves. So that friction is generating heat. And that is exactly what happened to SOAR. As it zoomed through the atmosphere at 7 kilometers a second, rubbing through all of that air, it generated friction and it got hotter and hotter and hotter. Now, as Dan already told us, we don't get fire in space, but it can still experience that intense heat. And eventually, it will start to melt, it will start to vaporize, and poor SOAR burned up. Now, the question that I always get asked, of course, is what about our astronauts? Because, of course, when our astronauts are coming back from the space station, we don't want them to burn up in the atmosphere. So we have incredible engineers who have designed something for our astronauts called a heat shield. So when our astronauts are coming back from the space station, they sit in a capsule in a spacecraft which has a special shield on the outside to protect them from the heat. And I have built my balloon its very own heat shield. Now, I will say that the heat shields that we have for our astronauts are a lot more sophisticated than the one that I've put on my balloon here. But what I want to show you is that by using a little bit of science, by doing a little bit of engineering, we can actually really change how things work. And this is something that you can try at home with some help. See if you can build a heat shield for your balloon that's even better than mine. So it's quite simple. What I've got in here is some cotton wool on the bottom. Then I've got a layer of foam over the top. And then on the very, very top, one of the most important bits, I have some tin foil. The same kind of tin foil that you might put over a chicken in the oven to stop it from burning, because that helps to reflect the heat away. And exactly like that, when our engineers build their heat shields, they use lots of different materials combined together to make sure that our astronauts stay safe. So, do you think my heat shield is going to work? Yeah. Oh, excellent. You've all got great confidence in me. I like that. Well, we're going to test it out because every good engineer has to test their solutions, has to test their inventions and make sure that they work. So I'm going to count this as a success if I can hold the flame against my heat shield for 10 seconds and the balloon doesn't pop. So will you all count with me so we can test it out? Yes? Okay, everybody ready to count? Okay, all right, we're going to start at 1 and we're going to count up to 10. And if we get to 10, our astronauts have made it back to Earth. Everybody ready? Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey! Phew! Thank you all very, very much. We've made it back safely. Thank you all for joining me. That has been a whirlwind tour of the life and death of a spacecraft. I hope you found that exciting and interesting. I hope you learned something. And before I leave you, I want to say that if you're excited about space, if you're excited about engineering, there is absolutely a job for you in STEM here. So I hope to see lots of you working on this in the future. I've been Ciara McGrath. Thank you very, very much.
Thank you so much, Ciara. I love that when Ciara said what her job is, someone at the back was like, yeah! I was like, it's a super cool job. What would you describe it as?
I design space missions.
I mean, come on. How cool is engineering? Right, it's my turn next to come up here and give you 10-15 minutes about my deep dive into the ocean. But first, I've got some stuff to clear up, bit of admin that I need to do on the stage. So let's watch another video from the Awesome Engineers videos. Here is when 12-year-old Iona met Roma on the Millennium Bridge.
Hi, I'm Iona, I'm 12, and today I'm here to find out a bit more about structural engineering from Roma Agrawal. You're a structural engineer. What does that actually mean? What do you do?
So my job is basically to make sure that structures stand up.
Okay.
So we're standing on this bridge, for example, and a structural engineer has done some maths and some physics to make sure that this bridge is safe, so that when you walk over it, it doesn't kind of collapse and send you straight into the Thames.
So what made you want to become an engineer?
So I always liked maths and science at school, and one summer I actually had a work placement where I had this really boring job, but all the people sitting around me were engineers. And they were designing the equipment that the physicists use to detect particles like the Higgs boson, which was incredible. And I thought, right, this is what I want to do.
So why are we on this bridge in particular?
So this bridge is quite an interesting bridge. So it was built in the year 2000, and it's called the Millennium Bridge, but it also had a slightly funny nickname, which was the Wobbly Bridge. And the reason it got that nickname was because when it first opened and people started walking across it, it started to wobble from side to side a little bit. And what I've got to show you is a demonstration involving jelly babies to explain how the different ways are that bridges can actually vibrate. So this is the infamous Jelly Baby Bridge, and I can assure you that many jelly babies were harmed in the creation of this structure. So the reason some bridges wobble is because of an effect called resonance. So what can happen, for example, is if you are a big band of soldiers walking down a bridge, you're all stepping and marching in step, and what can happen is you start to resonate the bridge so that it starts swinging like this. Or you might, like on the Millennium Bridge, make it move side to side. And when that started happening, because the bridge was moving from side to side, people started stepping in exactly the same frequency as this bridge was moving. And then the third one is also when you get the wind blowing onto a bridge and you get it resonating in a different way, like this, kind of twisting up and down. And these effects are not very good for bridges because it basically makes them crack or move or makes you feel unsafe. So we have to, as engineers, make sure that these kind of things don't happen.
So thank you so much for telling me all this. I've definitely learned a lot about engineering and I will consider it in the future.
That's fantastic, Iona. You're very, very welcome.
Thank you, Iona and Roma. Now I just want jelly babies. It's a good challenge to try to make those. It takes hours to make one of those jelly baby bridges. A lot of fun. So it's my turn to tell you about some very awesome engineering. And I want to today take you on a dive into the deep ocean. I'm a scientist. I'm a scientist by training. I'm a science journalist. I make stuff on TV and YouTube and radio. But I'm also a bathynaut. What's a bathynaut, Greg? I think if you knew, you'd be more excited. Okay, have you heard of the term astronaut? Oh, right, that one gets a reaction. Okay, so let's work out where the name astronaut comes from. So, astro comes from the Greek astron, which means star. And naut comes from the Greek nautes, meaning voyager. So an astronaut, that is someone who goes and voyages through the stars, which is kind of lovely. A bathynaut, well, bathy means the deep. So a bathynaut is someone who voyages through the deep. And actually, this is a photo of me. That's me. If you ever get to go into the deep, dark ocean, don't wear a deep, dark top. Because then all the photos, you can't actually see yourself. You can just see the pilot next to you. But don't worry, I've got some videos to show you instead. So I want to introduce you to the amazing engineering that allowed me to go down into the deep, dark ocean. But we're going to start with a bit of history. We're going to look back and meet the first two bathnauts, the first two people that ever went down deep in the ocean. William Beebe on the left. He's like Sir David Attenborough. He wants to go out and look at the life around him, right? Otis Barton is an engineer. And Beebe challenged Barton to make them something to take them both down into the deep ocean. What did he make? Well, first, in engineering, you find a problem and then you find a way to solve it. So the problem is, how are we going to get down there? So what they did was Barton went, okay, what have we got around at the moment? So submarines. Submarines could go as far down as 117 meters, which is the same depth of about 1 and a bit Big Bens. So if you take one Big Ben and then a bit of a Big Ben, that's how far down a submarine could go. But a submarine doesn't have windows. And Beebe wants to be able to look out at the life in the deep, dark ocean. But there was another way that people were going down into the ocean in an armored suit. How cool are these things, right? You basically step into it, right? And they're really big and heavy. So they're really cumbersome, really hard to move in. But you can see the world, but they're not exactly particularly comfy. That could go down a bit further, 160 meters. So what's that? Almost 2 Big Bens down. But neither of these options worked. But Barton took inspiration from them and he came up with this. This is called the bathysphere. There's that bathys for deep again, the bathysphere. It has windows. You can see them. Now, what you're looking at the front is actually the hatch. That's the way they get in. But at the back, you can see 2 windows about the size of a hand. But let's join them on this journey. 90 years ago, the year is 19... Oh, come on. There you go. The year is 1930. They've climbed into the bathysphere. The hatch gets put on, closed inside. And then you see that cable coming out of the top. They're kind of hung by that cable, splashed into the water. That's them there, ready at the top of the sea. And then that cable is then released, and they go down, down, down into the ocean. You see the cable going off to the right? There's two things in that cable. One is a power line, because they've got a light, and they hold a light to one window, and they put their face to the other window, and they wait until something swims past. And it reflects that light, and they can see it. And the second thing that's in there is a telephone line, so they can actually talk to the people up the top. Hello, topside, we've just seen a fish. So I think that's pretty neat engineering already. And they go down, 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 and they reach a depth of 245 meters. I want you to remember that number, 245 meters. It's 2 and a bit Big Bens. Where did they do this dive? They did this dive here. Anyone know where this is? Any ideas? This is the island of Bermuda. And if you type Bermuda into Google Maps, you see this. Doesn't really help. You zoom out, you see this. Doesn't really help. You zoom out again, and finally, that helps a little bit. It's about 700 and a bit miles from New York, 1,000 miles from Miami, 3,000 miles from Cornwall. So now you can work out where it is, if you ever get lost. So that's where Bermuda is. Why did they dive off the coast of Bermuda? So you can see this is the island at the top of the Bermuda Island, but if you peel off the surface of the water, you can actually see now what's underneath the water. And what this shows us is there's not 1, not 2, not 3, but 4 underwater volcanoes. They formed 33 million years ago. We don't call them underwater volcanoes, we call them sea mountains or seamounts. So these brilliant 4 seamounts there, and they wanted to go dive in Bermuda. And what's even cooler is that's where I got to go dive. So I spent a month on this boat, on this research vessel called the Baseline Explorer, going around Bermuda, and the teams were diving every day. So let me introduce you to what we were diving in. It wasn't the bathysphere, it was these submersibles here. There are 2 of them. Each one is worth more than $2 million. And then you add all the science kit as well. Yeah. And they are incredible bits of engineering. And I'm going to introduce you to a little bit of that now. Shall we dive? Yeah. Rubbish. Shall we dive? Yeah. Nice. Oh, I'm excited. Let's get down there. Hello, sir. Can I come in? Yeah. Oh, it is a bit small, isn't it? All right. See you topside.
Yeah, I think we're ready to slide you into position. Okay.
Oh, we're flying. Yeah, let's turn this on. On that side, is it? We're in. I guess we're ready to go then.
Yeah, good, thank you. Oh, it's so good to be in here. I've been waiting for this for such a long time.
Fantastic. So they're starting to release straps now. Roger that, doing a thruster. So I'm going to test my thrusters.
There's Kenny. Kenny is the swimmer. Oh, that's my first glimpse
of underwater.
That is my first glimpse of the underwater.
You're off the hook, and good luck on your journey to the deep.
Roger that. Here we go.
Thank you, Jeremy. Okay, so we've been kind of dropped off the back of the ship, off the big A-frame. We're splashed in the water. We're ready to dive. But let's just pause it a second before we dive. So we are, right now, that's pilot Kelvin and me, and we're floating. Another way of saying that is we say we're buoyant. So we are buoyant right now. And during this whole journey, we're going to need to control our buoyancy to sink down and rise back up again. And we're going to do that using these things called the main ballast tanks. They're at the side of the sub. Here's a schematic. You can see how big they are. They're nice and big. Right now, they're full of air, and that's why we're floating. I want to do something to the main ballast tank so we can then start to sink. What should we do? Any ideas? Yell it out this time. Any ideas? Let the air out. Good. Okay, we'll do that. What should we replace the air with? Water. Genius, because there's quite a lot of it around. So you open the valves at the top of the main ballast tanks, the air comes out, water goes in, that makes you a lot heavier, it changes your buoyancy, and then you can start to dive, slowly and carefully. Shall we dive? Yeah, we shall.
Roger that. Opening vents now.
Okay, so tell me what happens as we open the vents.
So you can see the air starting to come out there.
Yep.
Right? And it's going to tip forward. And then it's going to roll back in a minute. So that's our start.
That's quite a scary feeling, actually, isn't it?
Yep.
We're going to meet another sub on the way down, and as we go down, look at what changes around us.
Topside, topside. This is Nomad. My depth is 24 feet. My heading is 240. My life support is okay, and my vents are secure.
So we just hover here for a little bit?
No, we're still going down.
Oh, we're going down?
Yeah, yeah.
You just can't tell at all?
No. So we're sinking.
Is that a co-pilot job, just to clean the windows?
Absolutely.
I can do that.
Yeah. Yeah, there they are.
That is a phenomenal sight. It's like they're flying.
They are.
Isn't it?
Yep.
Whoa! Yeah, hi guys, we see you. Oh, that's so awesome. So, what do you see? What did you see change in the world around us as we started going down? Yell it out. It got darker, yeah. Now, the science of that's actually really, really simple. Water scatters light. So the more water there is as you go deeper and deeper, the more light has been scattered. For the nerds in the room, my people, what also happens is the water also absorbs some of the colors of light. Red first, and then down the spectrum. So actually the world gets bluer as you go down. You'll see that as well. So let's fast forward through the next bit as we start to go down. It takes us like an hour or so. And you can see the world getting darker and darker and darker and bluer and bluer and bluer. Now, when we started the dive, we were up in the sunlight zone at the top. Lots of light, lots of life. And then it gets darker and darker, and at 200 meters down, we move into the next zone called the twilight zone. When we're in the twilight zone, it's much darker. But it's not just the darkness that's a challenge when you're in there. Here's Calvin and I, we've just crossed 200 meters. There's something else that makes life really hard as well. The pressure. All that water around us, all that water on top of us is squashing us. And actually, at 200 meters down, it's like having an aeroplane on top of the sub. There's that much pressure on top of the sub. So I asked Kelvin, why don't we just get squashed? Tell me about this incredible machine. How can it survive those massive pressures?
Well, we're in a perfect sphere. So this is an acrylic sphere, and it is built to handle that pressure. So if it was square, the sides would be pushed in, but because it's a perfect sphere, it doesn't crush. It pushes in on itself and actually gets quite strong.
Clever engineering, I tell you. So here we are. We've been traveling down for quite a long time. What depth are we aiming for? Well done those of you who remember. 245 meters, because that is the depth that those first bathonauts ever got diving in this same place. Really lovely. We were like following their bubbles down. Oh, it's very poetic. So we were about to get there. We hit our depth of 245. We'd made it. Then this happens. Oh my word, what's that?
That's the wall right there.
Oh my word, this is phenomenal.
Topside, topside. This is Nomad. My depth is 832 feet. My life support is okay, and I'm with Nemo.
So what's that? That is the side of the seamount, one of those underwater volcanoes that formed 33 million years ago. We've gone down to that depth, and we're at the side of the seamount. Now the science starts. We start taking samples, we start taking videos, we start looking at the life that's around us. They're going backwards and forwards on this seamount. They're seeing spiraling wire coral, big lumps of rock covered in all sorts of stuff, fish. I think it's an angelfish you just see at the top there. And one of these. Oh, moray eel.
Oh, moray eel. Green moray.
Check that out, look, a green moray eel. This far down, that's amazing. Wow. Never seen one that far down before. All that spiral wire coral, actually. Super cool trip. So much I could tell you about it, but we don't have time. So I'm just taking you just down that far. That's actually the maximum depth that those subs can go to, 1,000 foot. So that was absolutely incredible. We've, of course, then got to get back up again. How do we go about doing that? Well, we control our buoyancy. We're going to replace the water. What are we going to replace the water with? Air. And the air is actually, we've carried that with us. We've got compressed air in the tanks below. We've also got oxygen in there as well. Kind of important so we can breathe while we're inside the sub. Anyway, long story short, pop back up on the surface. One of the most amazing things I've ever done in my life. And all thanks to some awesome engineering. And I was there to do some amazing, amazing scientific research. So that was super cool. So if you lot are interested in science, technology, engineering, or maths, look at the sort of places that STEM can take you. So many cool, exciting jobs. Anyway, thank you very much. It was a pleasure to tell you about my dive to the deep. We've only got 5-10 minutes left together, and we need to fit in an end-of-show fun game on the stage. So what I'm going to do is I'm going to set up for that. I'm going to show you a quick video while I do it. So I'm going to introduce you to Lorenzo, Madeline, and Joshua, who interviewed a whole bunch of awesome engineers about what they get up to in their day job. Check this out.
What do you do?
I fix an airplane called a tornado.
I'm actually a biomedical engineer.
I work on some very special planes that go all the way into space.
Did you always want to be an engineer?
Yeah, I think I did. I was like you. I used to take things apart.
This is what I built. We call it the Neuro Ball.
What did you want to be when you were little?
I wanted to be an astronaut. Yeah, so I wanted to go into space, and I still do. I still want to go.
Does Superman fly faster than your jet?
Superman? Now then, I think he flies faster than airplanes.
How do you go to the toilet
How do you go to the toilet? So, when you're going to space, they actually put you in a nappy. Whereas when you're up in space, you float around, don't you? So you have to actually strap yourself down to the toilet. You can't have a shower either, so it's a bit smelly up there.
I am not going to space.
Feels kind of soft and kind of hard. What made you think of something like that?
My uncle had a stroke. He was not able to move his arm, and that was really sad for me. He is actually getting better. Would you buy one?
If I had a stroke.
Hopefully, that's not going to happen.
How could I be an engineer?
You basically need to find a problem that you really want to solve.
Why is engineering exciting?
Because we get to build some amazing things. So you know when you see a plane in the sky and it flies across, and engineers made that? Yeah, I know, and that's what engineers get to do.
Should we salute them? Yeah, great. Yeah.
High five.
Love that. Super cool, very cute. So there you go, it gives you a great example of the variety of the different types of jobs, the creative, exciting jobs in engineering, right? You've got someone who's helping someone who had a stroke. You've got someone who's sending planes into space. Engineering can take you into all sorts of different areas. And as Gilliam said, to be an engineer, all you've got to do is find a problem and then think up a way to solve it. That's all you've got to do. Spot a problem. So always go around looking for problems and find ways that you can solve them. Shall we do an end-of-show fun game? Yeah. Okay, cool. Right. I want to show you some simple engineering that you can do at home. It's one of my favorite things. It's how to make one of these. Woo! It's a ping pong cannon. They're really simple to make at home, and I recommend you do give it a try. All you need a paper cup, and then you need to remove the bottom of the paper cup. So you could do that with a pair of scissors, with some help, of course, being super careful, health and safety, tick. Or you can push your thumb in and just rip out the bottom, so you can look right through it like that. Then you take a balloon and you tie a knot at the end of the balloon, in the neck of the balloon, like that. And then, very carefully, you chop the end of the balloon off, so the top of the balloon, so it's like that. And then you stretch that over the hole. Where's the hole gone? It's there. You lose a hole because you can't see it. Hey. All right, you stretch that over the end like that, and then take some tape, and you tape around your balloon. You can be a bit more careful than me, and you have yourself a ping pong cannon. Should we try it again? Yeah, okay then. Let's do one more of this side. So I thought, why don't we have a bit of fun with a ping pong cannon? Always looking for games that you can play with these sorts of things. So I am looking for 3 volunteers to come up on stage. You don't know what you're going to do yet. Might be putting you in a shark tank, which you're going to still volunteer for. Sure, yeah, I get it. So would I. I'm going to do 3 volunteers up on stage to play a quick game with the ping pong cannons. Deal? Deal. Okay, can I have some house lights? Let's see if I can find some people. Okay, all right. I am going to take, vying over there, I'm going to take person in the, is it a Chelsea shirt? Come on up. That's one that side. Is there on this side? Can you come up? Yeah, you. Yeah, me? What? I can take one more person. Who's it going to be? Oh, no, this is always really hard. Who am I pointing at? You! Come on up. Hi, how you doing? You all right? Just pop yourself behind one of these bins. Wait for the other two. Hello. Come across the stage. Watch the trip hazards. Nice one, nice one, nice one. Right, you've each got a bucket of ping pong balls. All right? You've also got a selection of ping pong cannons. So if one breaks, you've got some spares there. All right? So there's one for you. There's one for you. There's one for you. And what we're going to do is we're going to take it in turns, okay? So you're going to grab one of the ping pong balls out, put it in your ping pong cannon, release it, and then you, and then you, and then we'll go back to the start. All good? What are you aiming at, Greg? What are we aiming at? You're aiming at me. Okay? I am the target. I'm going to try to catch as many of your ping pongs as possible. Let's see what happens. Let's have some music. Okay. It's friendly competition. Okay, you're first. Go for it. Not the face. Oh, okay, a little bit harder next one. Whoa, nailed it. Right in my chest. Okay, good job. Oh, okay, that was round one. That was practice. Great, got it. Yes, nice. Nice. 3 for 3. Got it on the bounce. Keep going. I'm going to go a bit further back. Oh, good job. Wow, you're amazing. Oh, that one I couldn't get, sorry. Even further back. Oh, yours flying off to the left. Okay, now we'll just start firing at the same time. I can do this. Just go, go, go. Let's hear some encouragement, audience. Come on. All at once. Go wild. Oh, got that one. Got that one. Oh, yes. Oh, no. Any left? Are we done? Oh, one more. Okay, one more. Make it count. Made it count. Huge round of applause for our 3 volunteers. You can all go back. Thanks so much. Who was that? Who was that? Give them a huge round of applause. That was fun. Whew, I'm out of breath. Just something you can try at home. And in the Marconi room here, there are lots of other activities you can go do. There's a paper plane challenge. There's all sorts of different things. There's also one of my other favourite games that uses the stretch and the bounce of a balloon. We call it Let's Go Bounce. And for this one, you take your balloon and you chop the neck of the balloon off. And then you stretch it over the top of a can, an empty can. Take that round and you have yourself a bounce pad like this. And then the challenge is to set up a tube, run one of the ping pong balls down the tube, and then position the bounce pad so it bounces off the top. And then take another bounce pad and position that where it lands. And then another one, and another one. And you see how many you can do. We managed to get 3 in an hour. And you can evolve this game. Some people are doing it with saucepans. Loved it, upside down saucepans. So anyway, have a play. Again, that's what engineering is also about. What STEM is all about. It's about having a play with these sorts of things. That is it. We're out of time. We're out of time. I've had a lot of fun. Have you lot had fun? Excellent. Do you feel we've shown you a whole bunch of exciting and creative jobs in science, technology, engineering and maths? I couldn't say it, but I'm glad. Who wants to be an engineer after today? Excellent stuff, excellent stuff. Remember, look, anyone in this room can be a scientist, technologist, engineer, or mathematician. Really, any of you in this room, anyone watching live, you can do that. And it's going to lead you on some amazing adventures wherever you go. All you need to do is find a problem and then come up with a solution. Easy as that. Thank you so much for joining me today. Thank you to the IET for putting on today and all the staff and everyone involved. Thank you so much. Thank you to my guests, Dangerous Dan and Kira over as well. For more on the wonderful world of engineering and technology, check out the IET's Engineer a Better World website. And also, there's loads of fun activities and info on there. We're launching a new competition soon. It's to design a backpack of the future. So that'll be a good one to get involved in. Get all the details there. Keep your eyes peeled. Lovely to see you. See you next year. Bye! Oh. If anyone wants to do a big group photo, if you want to be in a big group photo, we're going to do that. We're going to come on the stage and do a big group photo. If you want to be in it, come on up. Give me 2 minutes to clear the stage though, all right? Thanks though, bye.